Hi, my name is Nathan Yahtzee, and my project is called The Microscope That Moves, Focuses, and Sees on Its Own. The main idea is that I built a low-cost automated microscope that can move a sample, focus itself, take images, and respond to plain English commands through Claude. So why does this matter? The reason that this matters is that microscopy is extremely useful, but can also be slow, repetitive, and hard to make consistent. If someone has to manually move the slide, adjust focus, change lighting, and take images, the results depend a lot on the user. Commercial automated microscopes can solve some of this, but they are often very expensive, with systems starting around $20,000. This project was meant to explore whether we could build a much cheaper version, usually using mostly 3D printed parts, a Raspberry Pi, motors, a camera, and software. The final system cost about $815, and the goal was not just to make a microscope, but to make one that feels more intelligent and easier to use. So how does it work? At a basic level, the microscope operates in four simple steps. First, a sample slide is placed on the stage, then motors move the slide in small controlled steps. A separate motor adjusts the focus by moving the optics up and down. The software compares images and chooses the sharpest one, so the microscope can autofocus without someone turning a knob by hand. Once it is focused, the camera captures the image. The hardware is built around a modified open flexure style microscope. Two motors control the movement in the X and Y directions, so the sample can be scanned side to side. A third motor controls the Z-axis, which is used for focusing. The microscope uses an 8 megapixel camera for imaging, and it has an RGB LED and filter setup so it can do both regular bright field imaging and fluorescence imaging. The Raspberry Pi is basically the brain that connects the software to the hardware. It controls the motors, camera, and lighting, and it also runs the interface that lets the user operate the microscope. The part that makes this project more interesting is Claude. Instead of the user needing to click every button manually, Claude can take a plain English request, interpret what the user wants, and turn that into a sequence of microscope actions. For example, a user can ask it to find a sample, focus it, and take a picture. Claude then plans the steps, and the Raspberry Pi runs the actual tools, moving the stage, focusing, changing the light, and capturing images. So Claude is not just a chatbot sitting next to the project. It is the layer that makes the microscope easier to control and closer to an intelligent instrument. The software also handles the normal microscope tasks in one place. The app shows a live camera view, controls movement, adjusts lighting, captures images, and runs autofocus. I also added color correction because the camera originally gave images a strong pink tint. After correction, the images look much closer to a real sample. The software also uses a micrometer slide to convert pixels into real distances, so measurements can be reported in micrometers instead of just pixels. To test whether the system worked, I checked several things. The microscope can move in very small, repeatable steps, down to about 1.56 microns. After repeated 500 micron round trips, the stage returned to within about 1.6 microns of its starting position. That means the motion was very repeatable for a low-cost system. The microscope also successfully autofocuses, corrects color, detects fluorescence, and can be controlled through a single app. Most importantly, it can respond to plain English commands, which supports the main goal of making microscope operations simpler. This section shows the actual images collected with the microscope. The bright field images include a blood smear, onion root tip, small intestine, and skeletal muscle. These show that the microscope can capture recognizable biological samples after color correction. The resolution target shows that at 10x magnification, the microscope can separate lines that are 4.5 micrometers apart. I also tested fluorescence using fluorescent particles in fluorescein samples. For the fluorescent dots, the RGB LED provides green excitation, and the emission filter helps block the excitation light while allowing the emitted fluorescence to reach the camera. In simpler terms, the particles absorb light from the LED and re-emit them at a longer wavelength, which makes them glow against a dark background. I also tested whether Claude could do more than just take a picture. In one test, Claude found and focused on a sample, built a mosaic image, and counted 12 pollen grains in under 5 minutes. Then, I compared Claude's measurements to image J. For several grains, the size measurements matched within 3.1%, and the largest grain had about 9% error. That showed that the microscope can connect imaging, movement, and analysis into one automated workflow. So, what did we learn from this project and what's next? Overall, this project showed that a low-cost microscope can automate many of the jobs that usually require a manual control. Movement, autofocus, color correction, fluorescence imaging, and image capture. It also showed that Claude can make the system easier to use by turning plain English instructions into microscope actions. The main limitation right now is that the system still needs better image stitching and object counting, especially when objects overlap. Another next step is to build a custom control board instead of relying on the current wiring setup as a more secure connection. The big takeaway is that this microscope is not just cheaper than a commercial automated system. It is also a step toward microscopes that are easier for non-experts to use because the user can describe the goal and the system can help carry it out. Thank you for your time, and I hope that you enjoyed this presentation.